Hello, welcome to 8.6 area between on normal curve. Yeah, I feel like I worded that funny. But anyway, we're looking at a normal curve, look at area between two values. I want to show you both how to do this with z-score table, and how to do this with the calculator as well, because both are fairly useful. And actually, I'm pretty sure we did it with z-scores already, but it can't hurt to go back through it again. So if you choose to do this using the z-score and table method, you will need to find two separate z-scores and their corresponding probabilities and subtract to find the difference between them. Yes, we did that before. If you use the calculator, you can set the lower and upper limits to the range of values you want to be between. All right, we got this. We got this. So number one, a set of laptop prices are normally distributed with a mean of 750 and a standard deviation of 60. What proportion of laptop prices are between 624 and 768? So, as normal, I of course love to draw our normal distribution curve. So I'm not very good at it, but I like to do it anyway. So 750, that's our mean. Standard deviation, 60. So that's going to be what, 810, 870, and then 930, and then 1, 2, 3, minus 60. So 690, 630, and 570. All right. So we're looking for the area between how the proportion of laptop prices between 624, which is like somewhere like right around there, um, and 768, which is probably something like here-ish, right? All right, so looking for the area between these two. Let's see if I can like color this in at all. Ooh, that's like kind of okay. I'll take it. All right. Of course, we could do the calculator, but that's the easy way. So I'm going to do that second. I like to do this just reminding you of the z-score process real quick. So we want the z-score for each one of these values. So z equals 768 minus the mean, 750, divided by standard deviation is 60. This is going to be 18 over 60. And 18 divided by 60 is 0.3. So 0.3 flat, so 30 if you want. We'll look at the z-score table for that in a moment. And the z-score for 624, so we get 624 minus the mean again, 750 divided by 60. So 624 minus 750 comes out to negative 126. Divide that by 60, and we have negative 2.1. Again, if you want negative 2.10. All right. We do want the z-score table real quick, so let's pull that up. All right. So let's not get lost. Well, let's get lost where I'm trying to be here. So z-score at or they're probably at 30.30. So 0.30 is this value right here, 6179. So we got, put it in green maybe, 0.6179. And then the one at negative 2.1, negative 2, just double check. Yeah, negative 2.10, negative 2.10 right here, 0.179. 0.0179, and we subtract these amounts together. Basically, we're taking the 6179, which is from this red line all the way over to infinity, minus the 0.0179, which is this red line over to infinity. So this part here, that I'm not going to shade in, but this part to the left of 624 is 0.0179. And then the part in between them will be that total 0.6179 minus that amount that we had on the left there, 0.0179. So we subtract them. find the difference between them. And we get, plain and simple, 0.6179 minus, oh, I guess it's just gonna be 0.6, no? I didn't even realize like the 179s are the same. So this comes out to 0.6, like flat. Now, that's we're done. That's 60% of the curve. So 60% of laptops are between $624 and $768. But let's use a calculator. Let's see how similar an answer we get with that. We didn't really have to do any rounding other than those probabilities, but should be pretty good with this. So second vars, normal CDF again. We're gonna go from, what do we say? 624 as our lower to the upper was 768. Double checking that. Mean was 750. And standard deviation was 60. Let's paste it. We get 0.60. A little bit. Not exact, but I mean pretty much exact, right? 0.60. So it works either way. Z-scores or calculator. I'm gonna use calculator for the rest of these. Just for the sake of time, you know, but yeah, Z-score table, also super duper useful. Let's look at the next one. What proportion of values are shaded? So this one obviously goes from 80 to 120. And I think this is based on the empirical rule because it doesn't say that this is one standard deviation, but I guess it's implied that this is one standard deviation. So if that's one standard deviation and this is -1 standard deviation, then this would be about 68%, right? But if we actually use the table or the normal CDF to just give it a second glance, we're going from 80 to 120, right? Yep, 80 to 120. With the mean of 100 and the standard deviation of 20. Should be about 68, yeah, 68.26, right? So that's the empirical rule at work there. About 68% is between the first standard deviations, right? And just to showcase it again, remember how 2 standard deviation was 95%? Well, if we did the same thing, but we went to 2 standard deviations, which in this case would be 60 to 140. You're gonna see 95%. And then one more time, just because I'm just in the mood for it, you know? If we went to 3 standard deviations, 40 to 160, it should be 99.7, 0.997. Yep. So there's your empirical rule. Again, just a reminder of what that was. Did that all the way back in 8.1, so it's been a minute, but yeah, I did want to just give you the opportunity to see it in play here using the calculator for the first time. So find the area under a normal curve that lies between z-score -1.5 and z-score of 2. All right, so this one's probably better to just use the table because it just tells us the z-scores right away. So let's go find them. So -1.5 flat is here, 0.0668. 0.0668. And the probability at 2, I guess 2 flat, right? Positive 2, 2.0 is 0.9772. 0.9772. And we subtract, we should always, by the way, when you're doing the z-scores, it's going to be the larger one minus the smaller one because you can't get negative probability. But yeah, if you take the 0.9772 minus 0.0668, you get 0.9104. So that one's pretty quick and easy with the table, but again, because I'm a fan of showing you everything, I'll show you this on the calculator as well. Now this one, what was it again? Are z-scores -1.5 and +2. Now remember, z-scores are always a standard normal curve where the mean is 0 and the standard deviation is 1. So mean 0, standard deviation 1, that's your standard normal curve. So these are z-scores. we paste it, you can see 9104. Same thing we got. Yeah, so don't forget that normal curve, remember, has a mean of 0 and a standard deviation of 1. So friendly reminder. Now, last one. The mean weight of adult American men is 180 with a standard deviation of 25 pounds. The weights are normally distributed. What percent of American men have weights between 130 and 205? All right, drawn out. We probably don't need to draw it out, but again, you know I like to do that. 180 in the middle, 25 pounds per standard deviation. So this would be 205, 230, 255. Then 3 backwards. So we got 155, 130, and 105. All right, cool. And we're looking for area between 130, which is smack dab at 2 standard deviations, and 205, which is smack dab at 1 standard deviation. So if you actually, there's so many different ways you can kind of estimate this. These are right on those actual standard deviation marks. That's at -2 standard deviations, is that 1 standard deviation. So you can use the empirical rule. Now, if you used the empirical rule to help you estimate, remember the empirical rule, each region here, 34% in this region, 34% in this region, and then 13.5% in this region. So if you actually use empirical rule just to estimate, you would get 34 plus 34 plus 13.5. Go back to all the way to 8.1 for this. And that comes out to 81.5. So I'll just put it in proportion form. So 0.815 is our estimated answer. Now, if we want to be a little bit more accurate, we can use the z-score table if we want to try that. So let's try it with z-scores real quick. So with z-scores, so I could already tell you that 130 has a z-score of -2 and 205 has a z-score of 1, but I'll show you the formula anyway. So 205 minus 180 divided by 25. This comes out to 25 over 25, which is 1. And then the other one, remember, is 130 minus 180 over 25, which is -50 over 25, which is -2. So, because I remember I could tell from my graph that it was at -2 standard deviations and 1 standard deviation, so you could do that. And if you use a z-table, if we go to 1 flat 1.0, it's 0.8413. So this one 0.8413, and then the one at -2, -2, 0, -2.0, 0.0228, and then subtract them. I'm basically doing this problem 3 times. What I'm going to do, by the way, 0.8413 minus 0.0228, and we get, when you subtract those, so z-scores 0.8413 minus 0.0228, you get 8185 equal to 0.8185. So again, a little bit off of the estimated one from empirical rule, but pretty close. And then finally, if you want to get the most accurate answer, we can use our normal CDF. And if we go to the calculator for this, right, normal CDF, our lower was 130, our upper was 205, our mean was 180, our standard deviation was 25. So this is obviously going to be the fastest way to do it of the 3 ways. But again, you get 0.8185 Well, that one's 0.8186 because it kind of rounds 0.8186. But yeah, I just wanted to showcase 3 different ways to estimate it. One, you could have used the empirical rule because it was perfect standard deviation marks. So that's one way to kind of quickly guess it. Another way is the z-score. Probably takes the most work to get the z-score, but it works just as well. And the easiest, probably where you don't really have to do too much thought, is just type in normal CDF and get that answer. So all 3 answers, as you can see, pretty much the same thing. All right, so just a good way to summarize all different types of ways to find or estimate the answer. All right, that'll be it for 8.6, guys. I'll see you in the last one, 8.7. Bye for now.